when we came to evaluating resilience and durability, we had to kind of define some of our own metrics, because it's not that you can go to Home Depot and buy 2 pounds of resilience. It doesn't work that way. We looked at air leakage reduction. We looked at avoidance of interstitial condensation, as well as the avoidance of mold and surface condensation, and see how these are different. We're going to talk about that. And then thermal resilience. So this is where we had to define some of our own metrics. Air leakage reduction, some standards use volume-specific requirements, including the IECC, Energy Star, the DOE Zero Energy Ready Home, Pretty Good House, and PHI. And some others, specifically FUSE, use surface area specific requirements. To be noted, we're going to see later how the FUSE core prescriptive have more stringent requirements compared to the performance-based FUSE 2021, as well as PHI has some additional surface area specific requirements for very large buildings. Now, this did not get included in this report because this report is about single-family homes. There's no actual requirements for California Title 24. What we used in the study, an ACH 50 of 4.4, was actually derived by the value set as default in the compliance software. But the standard itself does not put a cap on the air leakage that the building has. Volume-related metric, ACH 50, these are the values calculated for each project. So for FUSE, that does not have an ACH 50 requirement, we calculated the ACH 50 backward from the surface-related values prescribed by each project. This is what it looks like. So the dark orange is PHI passive house, the light orange is low energy building, PHI low energy building. The light blue, the blue, solid blue is FUSE 2021 core, and the white dot with the blue line circle is the prescriptive FUSE, which is required to be more airtight than the FUSE performance-based. Looking at the surface area related metric, this is the table we calculated. For the non-FUSE project, FUSE is the only one that requires the surface area, the surface related metric, and for the non-FUSE projects, we calculated that backward from the ACH 50 values. This is what it looks like. The blue dots are FUSE performance-based. The white dots with the blue line are the FUSE prescriptive. You see some are missing because FUSE prescriptive has the requirement for the surface area per bedroom. And then you have the surface-related converted values for PHI passive house in dark orange and the PHI low energy building in light orange. And you see that in general, PHI passive house is more stringent than FUSE, both of them. And the low energy building kind of depends on the size. Now, looking at the airtightness results, looking at the average value for the volume related, this is what it looks like. The most stringent is PHI passive house with 0.6 ACH 50 value maximum. The least stringent is the California Title 24 with 4.4. And you can see that once you convert to volume related metric, FUSE numbers look less stringent than PHI low energy building. Now, looking at the same values for the surface area related, it's the same metrics. This is not about talking which one we should be using, surface area or volume related. This is comparing the standards across the board with the same metric. So with surface related metric, PHI's passive house is the most stringent with 0.034 average cubic feet per minute per square foot. And you can see that the second most stringent is FUSE prescriptive, because FUSE prescriptive requirements are more stringent than the regular fuse. Talking about thermal resilience, this is something, the two pictures here. The bottom one is the Icebox Challenge event in Denver, Colorado in 2023 for the PHM conference in Denver. They built a box to comply with code minimum, and then they built the same box to comply with passive house. And they measured the amount of ice lost over a week or two. And consistently, you can see that passive house, being better insulated, also loses less ice over the same amount of time. At the top, you see a picture from EMU's own builder training. And these boxes that you see next to our black EMU trailer are the passive pods that we designed to teach builders about different passive building construction techniques for both commercial and residential buildings. And once the participants are done with air sealing and insulating the pods, we heat them up for a certain amount of time, as it is shown in the graph on the top right-hand side, and then we unplug them, we roll them outside and let them cool down overnight. And whichever stays the warmest wins that competition because it's the one that is better sealed and better insulated. So that is also the most resilient pod. Now, this is, for the purpose of this study, we try to convey this concept of thermal resiliency, and we did that by calculating the heating and cooling loads for each project. The idea was to try to understand how the building performs. The two pictures here, the photo and the infrared camera image, come from IFA, the International Passive House Association, and they explain pretty well the concept of passive house in turning the building into a thermos. A thermos is so air sealed and insulated that it stays warm or cold for a long period of time without adding energy, whereas the coffee mug needs to be constantly heated in order to remain comfortable. So we took this concept, we looked at the heating load, and we came up with the inclusive R value. It's a parameter that we made up for this study in order to try to replicate what was happening in the passive pods. And the inclusive R value is intended to represent the thermal protection of that the building envelope has. It's also a good way to compare building standards with each other because, for example, in different versions of the IECC, they may improve or increase the amount of insulation you have at the ceiling, but they may have a higher allowance for leakage. So how do you compare the two? The inclusive R value can help you with that. The inclusive R value is pretty much 1 divided by the total heating load divided by the envelope area times the delta T, the reference design temperature used for the heating load calculation. The results shown in the table here, it's very small, but you can see that there's a little bit of improvement from the 2018 to the very left, from the 2018 to the 2021 energy code, and the improvement to the 2024 energy code is almost negligible. All in, the inclusive R value average for all the windows, all the doors, the air leakage, the heat recovery for the ventilation, and all of that, for the 2018 code is about an R11. It's about an R12.6 for the 2021 code and 12.7 for the 2024 code, all the way to an R35 for the PHI passive house. And that it allows you to understand how much more resilient a PHI passive house is compared to the other standards. Now, in terms of if benchmarking against the 2018 code, the R value, inclusive R value for the 2021 goes up about 8%. It's about 9% better for the 2024, but it is about 3 times better for PHI passive house. and vice versa. If we benchmark against PHI passive house, you see that the other passive stands at about 70% of that inclusive R value. Anyway, this was a way to try and convey what the thermal resilience, a way to measure the thermal resilience. It does not account for thermal mass, which in residential buildings is pretty negligible compared to the importance of the impact of thermal mass is negligible compared to the impact of insulation, air sealing, good windows. There's plenty of research by PHI on this method. It was a way to kind of convey that. Looking at the score for resilience and durability, we talked about air leakage reduction compared to the 2018 code. It protects from moisture management, from moisture damage, that is air exfiltration. We looked at the avoidance of interstitial condensation, that is what all building standards have. And this is basically the interstitial dewpoint that even building code includes. The avoidance of mold and surface condensation, on the other hand, that is what the picture showing mold in that room refer to. It's avoidance via analytical method and protects from moisture damage at the surface. And that is what PHI has and Fuse partially has. Then the thermal resiliency, what we were just looking at, by means of the inclusive R value, and the building can remain comfortable if the heating and cooling system or the grid fail. And this is what the score looks like when we compare these parameters for resilience and durability.